Welcome to a video on half-angle identities. The goal of this video is to use half-angle identities to determine function values. So here we see all of the half-angle identities. Notice a lot of these seem very similar, so be very careful when you copy them down. Notice that the first three have a plus or minus sign on them. What this tells us is that we have to determine whether the function value will be positive or negative based upon the quadrant of angle A over 2. I did include the derivation of these identities. We don't have time right now to go through them, but you may want to pause the video and see how we can obtain these formulas. And the next slide also shows how to find the half-angle identity for a tangent. Again, notice that it comes from taking sine of 1/2 theta and dividing by a cosine 1/2 theta. But let's go ahead and take a look at some problems. Here we want to determine the exact value of sine pi over 8. So we know we're going to use this identity. The first thing we should do is find the value of angle A. There's a couple ways of doing that. We want A over 2 to equal pi over 8. So if we perform cross products, we'll have 8A must equal 2 times pi. Dividing by 8, we can see that A must equal 2 pi over 8, or pi over 4. So when we set this up, we're going to have the sine of pi over 8 equals the sine of pi over 4 divided by 2. So we're going to use pi over 4 for angle A. Another way to think of it is if we want pi over 8 to equal A over 2, we'd have to double this and then divide by 2 for them to be equal. Okay, so subbing this into our formula, we're going to have plus or minus the square root of 1 minus the cosine of angle A, which is pi over 4, which is good news because that's one of those reference angles, and then divided by 2. So if you don't have your unit circle handy, we should sketch pi over 4 in standard position. It's actually a 45-45 right triangle. So the cosine of pi over 4 would be 1 over square root 2, or if we rationalize that, we would have square root 2 over 2. So we'll have 1 minus square root of 2 over 2 all over 2. Now let's clear the fractions in the numerator. So we're going to multiply the top and the bottom by positive 2 underneath the square root. When we do this, we'll have 2 times 1, that'll give us 2, minus square root of 2 divided by 2 times 2 will give us the square root of 2, and then 2 times 2, of course, is 4. Our last step, since pi over 8 is in the first quadrant, we know our function value will be positive. Next, the square root of 4 would equal 2, and then our numerator does not simplify. And we have now found our function value that we were looking for. Sine of pi over 8 is equal to the square root of 2 minus the square root of 2, all divided by 2. Let's go ahead and check this on the graphing calculator. Here you can see I've compared the sine of pi over 8 in radians to the exact value that we found, and they are the same, which verifies our work. We want to find the exact value of cosine 105 degrees, so we'll use this identity. Again, if we want A over 2 to equal 105 degrees, we'd have to double this. So 210 divided by 2 will give us 105 degrees. So we're going to use 210 degrees for angle A. Again, if we don't have our unit circle handy, cosine of 210 degrees, that would be 30 degrees past 180. Makes this a 30, 60, 90 right triangle, so we have 1, 2, square root 3, but both the x and the y coordinates would be negative. So the cosine of 210 degrees would be the adjacent over the hypotenuse, or negative square root 3 over 2. Next, let's clear the fractions again, so I'll multiply the top and the bottom inside the square root by 2. Well, 2 times 1 would be 2, 2 times square root 3 divided by 2 would be negative square root 3. And then 2 times 2, of course, is 4. And then lastly, 105 degrees falls in the second quadrant where the x-coordinate would be negative, therefore the cosine value would be negative. So this will be negative. The square root of 4 would give us 2, and the numerator does not simplify. We have the square root of 2 minus the square root of 3. And there's our function value. Okay, we have one more question. Here we're given cosine A is equal to negative 2/3 in the second quadrant. We want to determine cosine A over 2, sine of A over 2, and tangent A over 2. First thing I want to make a note of is angle A is in the second quadrant, which means it's between 9 degrees and 180 degrees. So A over 2 will be between 90 degrees and 45 degrees, which means it's in quadrant 1. What that tells us is all of these function values will be positive. So let's just make a note of that here. All function values will be positive. Next, let's go ahead and sketch this angle in the standard position. We're in the second quadrant, so here's our reference triangle, and this reference angle has a cosine value of negative 2/3. Using the Pythagorean theorem, we can determine this third side of this reference triangle, and it will equal the square root of 5. Let's go ahead and try to find these function values. Cosine of A over 2 is equal to the square root of 1 plus cosine A, which is negative 2/3, all over 2. Remember, we already determined all these would be positive. Let's go ahead and clear the fractions. Our denominator would be 6. The numerator would be 3 plus negative 2, which would give us square root of 1/6, which is equal to 1 over the square root of 6. And if we rationalize this, we have the square root of 6 over 6. Let's go ahead and try to find the sine of A over 2. We have square root of 1 minus cosine A, so 1 minus negative 2/3, all over 2. Again, clearing the fraction. By multiplying the top and the bottom by the denominator 3, we'd have 6 again in our denominator, and here we'd have 3 plus 2, which equals the square root of 5/6, which equals the square root of 5 over the square root of 6. We rationalize this, we will have the square root of 30 all over 6. And we have one more. We want to find the tangent of A over 2. Notice we have a variety of options here. I'm going to go ahead and use the last one this time. Of course, if we have sine of A over 2 and cosine of A over 2, we could just find the quotient of the two. But I'll go ahead and use the identity 1 minus cosine angle A, which is given as negative 2/3, all over the sine of angle A. Going back over to our reference triangle, the sine of angle A would be opposite over hypotenuse, or square root of 5 over 3. 1 minus negative 2/3, that would work out to 5/3. And then instead of dividing by the square root of 5 over 3, we'll multiply by the reciprocal. This simplifies nicely. So we have a function value of 5 over the square root of 5, which is correct, but we'll rationalize it one more time. So we have 5 square root of 5 all over 5, which simplifies to square root of 5 for the tangent of A over 2. Okay, that was quite a bit of work and a lot of algebra involved, so be very careful when you work through these problems, and I wish you success. Thank you for watching and have a good day. We want to determine the exact value of sine pi over 12 using a half-angle identity. The most common two half-angle identities for sine and cosine are given here, though some textbooks do refer to these power-reducing formulas also as half-angle identities. For this example, we'll be applying this half-angle identity for sine, though in the next video we'll find the same sine function value using this equivalent identity given here. Let's begin by determining the value of A, as well as whether the sine function value will be positive or negative. Now it might be tempting to convert pi over 12 radians to degrees. Of course we could do that. Pi over 12 times 180 degrees divided by pi Notice how the pi's would simplify out. We'd be left with 180 degrees divided by 12 equals 15 degrees. But for practice, let's go ahead and leave this in terms of radians. So notice that a over 2 must equal pi over 12 radians. So if a divided by 2 is equal to pi divided by 12 radians, to solve for a, which we need on the right side of our identity, we would multiply both sides by 2. So a is equal to 2, or 2 over 1 times pi over 12 radians. We have a common factor of 2. There's 1, 2, and 2, and 6 2's and 12. So a would be equal to pi over 6 radians. So applying the identity, we know that sine pi over 12 is equal to the sine of pi over 6 divided by 2. And now before we apply this identity, let's determine whether the sine function value is going to be positive or negative. Well, since pi over 12 radians, or 15 degrees, is in the first quadrant, where both x and y are positive, and sine theta is equal to y over r, we know r is always positive, and now we know that y is positive, and therefore the sine function value is going to be positive. And as we know, all of the trig function values are positive in the first quadrant. So we know we'll have a positive square root, and then we'll have 1 minus cosine a, which now we know is cosine pi over 6, and all this is divided by 2. Notice how the denominator of 2 is underneath the square root. And now for the next step, we'll determine the value of cosine pi over 6. So we can use either a reference triangle or the unit circle, and let's show both. Pi over 6 radians is equal to 30 degrees. So in standard position, this is the initial side of the angle. The terminal side would be approximately here, where again the reference angle is pi over 6 radians, or 30 degrees. So if we sketch a reference triangle, we need to recognize that we have a 30, 60, 90 reference triangle. So we can label the short leg 1, the hypotenuse 2, and the longer leg square root 3. So using a reference triangle, cosine of pi over 6 radians is equal to the ratio of the adjacent side to the hypotenuse, which would be square root 3 divided by 2. And of course we can check this trig function value on the unit circle. Here's the terminal side of pi over 6 radians, or 30 degrees. And because we have the unit circle, x equals cosine theta, so cosine pi over 6, or cosine 30 degrees, is square root 3 divided by 2. Which means we now have the square root of 1 minus square root 3 divided by 2 all over 2. Now let's simplify this. Looking at just the numerator, we can clear the denominator of 2 by multiplying by 2. But if we multiply the numerator of a fraction by 2, we must also multiply the denominator by 2. Notice how this is equivalent to multiplying by 2 over 2 underneath the square root. So now we have the square root of, when we distribute, we have 2 minus square root 3 divided by 2 times 2. The 2's would simplify to 1, leaving us with just minus square root 3. And our denominator would be 2 times 2, or 4. And now because we have a fraction under the square root, we can write this as the square root of the numerator over the square root of the denominator, which is the square root of 4. And the square root of 4 simplifies to 2. So this leaves us with the square root of 2 minus square root 3 divided by 2. Now let's check this on the calculator. We'll first convert this to a decimal, and then approximate the value of sine pi over 12 on the calculator. Let's put the numerator in parentheses. So we have open parenthesis, second x squared for square root, and then 2 minus square root 3, right arrow, close parenthesis, divided by 2, enter. And now we'll compare this to sine of pi divided by 12. Let's first make sure the calculator is in radian mode. So we'll press the mode key, go down to the third row, highlight radian, press enter. And second mode for quit, and now we'll press sine pi divided by 12, and notice how this verifies our work is correct. There's one more thing I do want to point out though before we go. We did find the exact value of sine pi over 12, or sine 15 degrees, using a sum of difference identity as well. Though the result did look different, it is the same exact value. So let's do a quick comparison. Again, we know that pi over 12 radians is equal to 15 degrees, which is also equal to 45 degrees minus 30 degrees. So if we compare the difference identity for sine, given here in red, we'd have the difference of these two products, which if we simplify, would be the quantity square root 6 minus square root 2 divided by 4. So using the difference identity for sine, this was the exact function value. And when we use the half angle identity, this was the exact trig function value. Again, they look quite different, though if we convert them to decimals, we can see they are the same. So depending on what method we use to find the exact value of sine 15 degrees or sine pi divided by 12 radians, the result will look different, but the function values are the same. I hope you found this helpful. In this example, we want to determine the exact value of tangent pi over 8 using a half angle identity. And notice that we have three options for the half angle identity for tangent. In this video, I'm going to use this last identity because I think it has the simplest denominator. And I think it's usually easier to apply these identities if our angle is in degrees. So let's start by converting pi over 8 radians into degrees. So we'll multiply by 180 degrees divided by pi. So notice how the pi's simplify out. 8 and 180 have a common factor of 4. There's 2 4s in 8, and there's 45 4s in 180. So this gives us 45 degrees divided by 2, or 22.5 degrees. So let's rewrite this as tangent 22.5 degrees, and then we'll double the angle to identify the value of A used here as well as here on the right side, which we actually had here before we divided. This is the same as tangent 45 degrees divided by 2. So A is equal to 45 degrees. Now we'll go ahead and apply this identity. This function value is equal to 1 minus cosine 45 degrees divided by sine 45 degrees. And we should already be familiar with this function value from the 45, 45, 90 triangle, where the two legs are 1 and the hypotenuse is square root 2. So the sine of 45 degrees is equal to 1 over square root 2, which rationalizes to square root 2 over 2. And because this is an isosceles right triangle, the cosine of 45 degrees is the same, 1 divided by square root 2, which rationalizes to square root 2 divided by 2. So we can rewrite this as 1 minus square root 2 over 2 divided by square root 2 over 2. Let's start by multiplying the numerator and denominator by 2 to clear the fractions in the numerator and denominator. So when we do this, our numerator is going to be 2 minus, again you can think of this as 2 over 1 if you want, so these 2 simplify out, so we have 2 minus the square root of 2 divided by, same thing in the denominator, these 2's simplify out, so we're left with square root 2. So the last thing we probably want to do is rationalize the denominator. So let's go ahead and rewrite this. We have 2 minus square root 2 all over square root 2. And now we'll multiply the denominator by square root 2 and the numerator by square root 2. So we're going to have 2 square root 2 and then minus 2 divided by 2. And then we can rewrite this as 2 square root 2 all over 2 minus 2 over 2, which simplifies nicely to square root 2 minus 1. Remember, when you're dividing by a monomial or one term, we can break it up into individual fractions. So the exact function value of tangent pi over 8 radians is equal to square root 2 minus 1. In these next two examples, we're asked to rewrite a trig expression using a half-angle identity. Here we have sine of 5x raised to the second power, so we'll be applying the half-angle identity for sine. So there's a couple things we have to remember here. First, notice how this function is being squared, so it's not a perfect fit. And if we want to rewrite a square root using a rational exponent, remember the square root of x is equal to x to the power of 1/2. So let's start by taking this half-angle identity and squaring both sides. And we'll also rewrite this square root using a rational exponent. So we'll have plus or minus, this will be 1 minus cosine A divided by 2 raised to the 1/2 power squared. The next rule we have to remember is when we have a power to a power, we multiply our exponents. So 1/2 times 2 is going to equal 1. And since we're squaring this plus or minus goes away because if we square a positive, it's positive. And if we square a negative, it's still positive. So we have the sine of a over 2 squared is going to be equal to 1 minus cosine A divided by 2. So the next step is to determine what is the value of A given sine of 5x squared. Well, 5x has to equal a over 2. So if we set a over 2 equal to 5x and multiply both sides by 2, we know that a is equal to 10x. So using the half-angle identities, a will always be twice the given angle. So now we have all the information we need to apply this slight variation of the half-angle identity for sine. We're going to have sine of 5x raised to the second is going to be equal to 1 minus cosine 10x divided by 2. And if we want, we could rewrite this as 1/2 minus 1/2 cosine 10x. So there's really not a lot going on here other than getting familiar with these new half-angle identities. Let's take a look at one more. Here we have cosine of 2x raised to the 4th power. So let's start by taking this half-angle identity for cosine and raising it to the 4th power. So we'll have cosine of a over 2, and we're going to raise it to the 4th power this time. It's going to be equal to plus or minus, and we'll also write this as a rational exponent again. So we'll have plus or minus, this will be 1 plus cosine A divided by 2 to the 1/2 power, and then again we're raising both sides to the 4th power. Well, here we're going to have 1/2 times 4, that's going to be 2. So we have cosine of a over 2 raised to the 4th. It's going to be equal to 1 plus cosine A all over 2 raised to the 2nd power. Again, notice how the plus and minus symbol is no longer needed because we're raising it to an even power. And remember, to square a fraction, we can square the denominator and square the numerator. So let's go ahead and multiply this out. Our denominator is going to be 4. If we multiply this out, we're going to have 1 plus cosine A times 1 plus cosine A. So we'll have 1 plus cosine A plus cosine, that's 2 cosine A. And then we'll have cosine squared A. Now we'll go ahead and apply this slight variation of the half-angle identity to the given expression. And remember, if a over 2 is equal to 2x, the angle in the half-angle identity, if we multiply both sides by 2, we'll have a equals 4x. So when we apply this identity, we'll have cosine of 2x raised to the 4th power is going to be equal to 1 plus 2 cosine 4x plus cosine squared 4x all divided by 4. And we could factor out the 1/4 to have 1/4 times the quantity 1 plus 2 cosine 4x plus cosine squared 4x. And of course we could also distribute the 1/4, but I think we'll go ahead and leave it like this. Again, other than doing some manipulations to these half-angle identities, there's not a lot going on here other than becoming more familiar with these identities.